So that would mean that the alternator is capable of 100 amps. So he is battery and the main bus. So now the alternator can supply the battery, or the battery can help supply power to the bus if you're more than that energy. I also have a 5 amp alternator field breaker. And then when I flip the switch for the master, right, the split master, and energize the alternator, I'm going to supply power to the over voltage protection and to my regulator. So again, the field, right, controls how much energy I put out. So if I put a meter in here, and I put a meter in here, at the moment, I'm only capable of 80 amps, right? Because I can't see how much I'm putting out. So I could put a amp meter in line, which would show me my plus and minus. And then I can put a load meter in the alternator. It would show me 0 and 100%. In this case, it has an over voltage light, right, to warn you that your voltage is too high. So looking at an Avionics bus, what you can do is you can have your main bus, which has your breakers also attached to it with your loads, and then the switch type breaker. So it has the handle. So usually switch type breaker, if it's feeding a bus, would be rather large, enough to handle all the items on this side. So you could have, again, 5 to 1, any kind of combination up to 20 amps. So therefore, if I want, what I can do is I can just turn off the switch breaker for avionics. I can apply ground power and then start the aircraft, whatever I'm going to do. Once it's stabilized, then I can switch the avionics master on and everything comes on. But there's one problem. We have to rely on who to turn off the switch breaker.
Pilot?
The pilot, yes, right? So if the pilot doesn't turn off the switch breaker, he's basically, there's no use to have the avionics bus, right? If he puts ground power on or starts the aircraft, he could possibly damage it. So what are we going to do? Eliminate the pilot, right? How are we going to do that? Well, we'll put a relay or a solenoid in on the avionics bus so that if the pilot hits the starter switch, he's going to put power to this solenoid and it will energize, and it'll pull the solenoid away and open up my avionics bus while the starter is engaged. Once he lets go of the starter, the relay will close, or solenoid will close, and then it would protect my avionics bus. If for some reason someone was going to plug in ground power, we're going to use the positive pin of ground power the same way. As soon as I plug the power cart in, the power was going to energize the plug on the avionics relay or solenoid, and it'll move the relay or solenoid and disconnect the avionics bus. Again, we don't want any spikes, right? High voltage spikes on the avionics. And this way it eliminates the pilot.
You're always trying to
there's the pilot there.
Yeah,
okay?
You're always trying to eliminate the pilot, aren't you?
Yeah, that's the easiest way to get around it.
I think everybody wants to eliminate the pilot.
So this, again, just shows you a different view of a bus system. So we have your avionics bus. We got radios, all your different radios. Your primary bus kind of gives you an idea too, right? Flaps, landing lights, strobes, beacons, fuel would all be a primary item you'd want. Again, you got your low voltage warning, your alternator breaker, alternator field. There's your split master again, the battery circuit with the battery contactor, and then a ground receptacle at the bottom. And then we go up to our amp meter, which is in series with the primary bus and in series with the battery. So we can see what's coming into the battery or what's going out of the battery. So moving into a little bit larger aircraft, we have more and more systems to deal with. So we could have possibly, right, twin engines, 3 engines, 4 engines, 5 engines, 6 engines. So typically, DC wise, we can have 1, 2, 3, 4, 5 buses. Same with AC. So we can have an AC bus 1, 2, 3, 4, 5. They like to use typically what they call an essential bus. So items that are essential. They could have an APU bus, stuff that just runs off of APU. Emergency bus, so that, again, in the event that there's an emergency, they don't want to have the pilot going through trying to figure out what he needs and doesn't need. So an emergency bus is fed normally and everything works, but in a failure of power, we use a diode to limit it to only the battery. So we'll show you that a little bit. Obviously, we want a battery bus, ground power unit. So if you have a DC ground power unit, typically they'll have a ground power bus, a ground power unit AC bus, and then typically lighting bus. Because again, there's a lot of lighting. There's instrument lighting, there's cabin lighting, there's floor lighting, passenger lighting. So again, there's all kinds of different systems once we get into large category aircraft. So looking here, and one of the things we want to do is we want to make sure that we can feed any system from any generator. So So first of all is your battery, right? Which is important. So you got your battery, and typically large aircraft, you'll have a voltmeter and an ammeter on that system. So the battery, you'll know the voltage and you know its amperage. So there's your essential bus. And again, typically always know the voltage on it. And again, you got a solenoid that's going to connect the battery onto your essential bus. And then from the essential bus, it runs over to your bus number 1 DC, then bus number 2. And again, each of them have their own voltmeter. And you'll notice we have what they call a bus tie circuit breaker. And we'll come back to that in a little bit. So in this case, it's a 3-engine aircraft. So we have 3 generators, 1, 2, and 3. And in this case, they are AC generators, not DC. So these are AC. So we notice we have voltage, we have frequency, and we have kilowatts of power that we're producing. So each generator, you can see the voltage, frequency, and power that it's producing. And we have a generator breaker. So once that's placed in, it is placed onto AC bus number 1. So from AC bus number 1, I can now engage the bus tie breaker, and I can feed pretty much all around the aircraft. And you'll notice now I have a bus tie voltage and frequency. Then what I can do is I can basically bring online generator 2 and 3, and I can feed those onto those as well. So now if I want, you'll notice it has a TR. So it says number 1 TR unit breaker. So if I push that in, it goes to TR number 1. And a TR, if you look, is the transformer rectifier. So the transformer rectifier is basically converting AC to DC, and it feeds into my DC bus. So I can use a transformer rectifier, or I can use the battery. So again, I have all these options to control the different buses. The selector typically selects what you want to look at. So usually it typically has 1 gauge, and you can select which unit you want to see. So you want to see number 1, number 2, or number 3 generator. External power. So if you plug in to the aircraft from external power, you'll notice it is on the AC bus. So it has to be an AC unit. So we got voltage and frequency, and we have an external tie. So to get it onto the bus, I can power the unit from a external power unit. So you have a battery charger, right? So we could run a battery charger to charge the battery if we need to. Your essential AC bus. So I think, I don't know if it'll work or not. Oops. So there's bus number 2. The batteries, essential. So the blues are AC. And there's my emergency bus. So the batteries can supply the power to the emergency bus. And you notice I put a diode in there. So current can only flow from the battery to the emergency bus. So if I'm powering the emergency bus normally, then it doesn't feed to the battery. But if I lose power, then I can feed the emergency bus directly from the battery. So these items would be preset. So you could have maybe COM number 1, nav number 1 are on the emergency bus. They work normally if the battery is, or if the emergency bus is being fed from the battery bus. And then in the case of an emergency, the battery directly feeds the emergency bus. So looking through electricity, electronics, or power plants, they do talk about the multi-engine aircraft if you're looking for more reading. With a single aircraft engine, again, only having one generator, the effect of it online or offline is typically minimal. So again, if it's online, it's going to be charging the battery and it's going to supply the aircraft with all of its electrical needs. That's why we did the electrical load, right? Calculating what it's using. If we lose the battery, if we lose the alternator, then obviously it's just going to use the batteries to supply the current for what we need. Again, that's why we did the emergency calculations for the battery. So when we get into two-engine aircraft, we have to look at more issues, right? We now have 2 generators or 2 alternators, and they can cause problems between each other. So in this case, what we want to do is we have to basically, we're going to go up in the difficulty level now, and we're going to look at what we need to control 2 generators or 2 alternators at the same time. So now what we need is we need to, right, equalize. We need them to both be doing their job and both carrying their own weight. So that's why we need an equalizing circuit. Reverse current cutouts. So we don't want the current to go backwards through the generators. So we're going to have to basically eliminate them out of the circuit when it's not in use. Current limiters. If we're going to run 2 units, we're going to have current limiters in there. If we over exceed that amount of current, the current limiters are going to basically blow. It's like a large fuse. So looking at the equalizing circuit, so we have 2 or more generators or alternators, and we're going to connect them in parallel, and that's going to supply us power. And again, we want the generators to share the load equally. So we're not overloading one generator or the other. So they both have to do the work. So if one is higher than the other one, what'll happen is the generator that's producing the higher power will take more of that load. So the first thing we got to do is make sure that the voltage on each one is correct. And what the equalizing circuit is going to do is it's going to control the voltage by using the voltage regulators. So we've already gone over voltage regulators, right? It automatically adjusts the field current to increase or decrease the power of the alternator or generator. So now what we're going to do is we're going to supply another bus, so an equalizing bus that's going to connect the two alternators together in the circuit. So what we're going to do is use a low resistance shunt. If you remember that, it's just basically a resistor that drops a voltage on it and the ground lead of each alternator or generator. So if we go back to this is our carbon pile regulator, right? So this is our generator and our field. So remember, we compress the carbon to make more resistance or less resistance. Well, now what we're going to do is we're going to add another coil on the bottom to be able to increase or decrease the voltage if one's higher than the other one. So here's two generators set up. So my equalizing shunt on both of them and goes through the voltage coil and it goes over to the equalizing bus. And then this equalizing bus is tied back, same idea. So both hooked up identical and both feeding the equalizing bus. So what's going to happen is the equalizing coil is either going to strengthen or weaken the effect on that voltage coil, depending on which generator is producing more output. And it's going to flow through the equalizing bus. So again, that low resistance shunt in the ground lead creates that potential difference between the negative and the generator and ground. So again, each shunt's created so that it will produce maximum potential of 0.5 volts that's generated across it at full output. So again, this is out of the textbook. So assuming one generator is delivering 200 amps, which is a full load, and generator 2 is only delivering 100 amps. So they're not equal. So under these conditions, generator 1 is creating a potential difference of 0.5 volts across the shunt. Just to make sure. See, you're awake? I guess no one is. So number 2 is only half output, so it's only 0.25 volts across the shunt. So if we look at the difference, we have 0.5 and 0.25. So we have 0.25 volts difference between them. So because they're connected to equalizing circuit or bus, we're going to get current to flow from one circuit to the other. So what's going to happen is current's going to flow through the equalizing coil of voltage regulator 1, and it will strengthen the effect on the voltage coil. It's going to cause more resistance. If you remember back, more resistance in the field of generator 1 will cause it to weaken the field, and the voltage should drop. When the voltage drops, my current should drop. On the other hand, the voltage is going to oppose the voltage coil on number 2. It's going to decrease its resistance, which will cause an increase in voltage and should cause an increase in current. So therefore, number 2 will begin to increase its voltage and take more of the current load. So they should equal out at about 150 amps each. So the carbon file and the vibrating voltage regulators both have a second voltage coil, again, to help when you're using twin engine or twin generator setups to help with that unbalanced. Reverse current cutouts or relays. So what happens is because generators don't have anything inside them to cause current to stop flowing, if I put current backwards, it will flow through the generator and could either damage the generator or your batteries. I don't think anyone's awake today.
I'm sorry.
Oh, look at there's Lynn. He just got kicked out and came back, I think.
Yeah, I did get kicked out. I just missed this equalizing bit here. Sorry about that, Brad, and everybody. This is for both a DC gen and an AC gen. Is that correct? This type of equalizing circuit?
This one is typically for the DC style.
So my Navajo, in other words.
Yeah.
Or my King Air, I suppose, eh?
Yeah.
Yeah, because once you go into the transport, you're mixing AC and DC, as you and I talked about back and forth on the buses, eh?
So yeah, if you go back to the AC one, typically what they'll do is they'll run AC generators and they'll convert it to DC. So you're not running a DC generator anymore, it's AC.
Yeah. Okay. Okay, so I'm just catching up to you. Okay, thanks, Brett.
All right. So what they want is they want to make sure that we have an automatic means, right? Again, eliminate the pilot. If we have to put a switch in there that the pilot always has to turn off before he gets out of the aircraft to disconnect the battery from the generator, most likely they'll forget and it'll either damage the generator or kill your battery. So again, one of the things they can do is a battery master. We can use diodes or we can use relays to disconnect the field. We talked about current monitoring, right? Looking at the amperage plus and minus. Again, the ammeter is right. Gives me indication if it's charging or if it's taking battery power. Remembering way back when we did shunts, so 50 millivolts would be full scale, and it can show what's happening, and it can also be used as a load meter if it's placed in the correct spot. So the load meter is typically showing you from 0 up, and that would be just what's coming out of the generator or alternator, or what load is on the generator or alternator. Voltmeters, again, typically we're looking at current, but sometimes you can have a unit that does voltage. So in this case, you got amperage on the top, and it says push for volts. So you push the bottom button in, and it'll give you the voltage of the system as well. So again, a handy system to see both.